Okay, so I'm going to give you some pictures about how to read symptoms of your local weather a little farther out, like 4 days out, or even 5 or 6 days out, as a kind of heads up. So here is a web address of a very interesting map of the whole Earth, of weather patterns on the whole Earth. It was designed by some people using NASA download data from satellites. And this map is updated every 3 hours. And if you play with it on a phone that might be a little low resolution, but if you play with it on a computer with a bigger screen, you can interact with that map to see weather systems developing over the Pacific that are actually your weather makers. So your weather is generated by the Aleutian low and the Hawaii high. And the position of those two air masses, if you go on that map and then scroll it so you're looking at the west coast of the US. You can play with it and turn it and move it. Usually, what comes up is an orthographic projection. You see streamlines of air that are rotating. That's updated every 3 hours. And they show you, that map shows you the position of the major air masses on the west coast. And the one that's rotating clockwise off of the west coast, that's known as the Hawaii high. And the one that's rotating counterclockwise up in the Gulf of Alaska, that's the Aleutian low. And the Aleutian low and the Hawaii high are the things that create the jet stream that feeds air into the continent that eventually gets to you. And the position of those two air masses determines whether you get a nor'easter or whether you get frigid weather or whether you get very benign warm weather. And watching that null school map in the morning or every couple hours, when you believe there's going to be something changing, allows you to kind of get a kind of heads up maybe 5 days out. And what I'd like to do is show you how to use that map along with the daily weather map that is in the newspaper or on your cell phone for the daily weather by explaining to you how the air masses operate. So a high pressure air mass, and I'll explain that now. That's what we're going to do today. A high pressure air mass rotates clockwise. And that means that the winds blow on the eastern side, they blow from north to south, northwest to southeast. And on the back side, they blow from southwest to northeast to give that clockwise rotation. And that is called a ridge or a blocking ridge. And the position of that blocking ridge, either on the west coast or on the continent, determines the extent and the force of any weather system that's coming into your area. And learning how to play with the blocking ridge, whether it's on the continent or off the ocean, or whether it's situated halfway off of your coast or further in, like in the Rockies, that determines the force of the system that's going to come to you. And what I'd like to do is give you some background on why that is so, because the clouds are continually giving you pictures of where the blocking ridge is and how it's operating. So here's a picture, a little bit of a recap from last. Warm air rises. And when warm air rises, it goes up. There's an equation that says for so many feet of rise, there's so much, I think it's 1,000 feet of rise, there's a degree of lowering temperature. So 1,000 feet of rise of warm air, that temperature at 1,000 feet is 1 degree lower than it is on the ground. And the higher it goes, the colder it gets. Warm air rises and cold air sinks. So if I'm a little guy here and I'm in a column of rising warm air, that warm air is rising, and when it gets up to 20,000 feet, it's 20 degrees colder than it is on the ground, and that will start to sink. It's kind of like a fountain. So the warm air rises and sinks and then falls and then comes back down and replaces the warm air that's rising. The cold air falls down around the warm air in a column and blows in. So the wind that's coming down blows in, and the wind that's going up blows out. That's called a convection cell. And there's a convection cell over a puddle. And the insects grab onto that. There's a convection cell over a tree or a forest, or here we have a convection cell over a mountain. So here I have a slope of a mountain with the sun hitting it, and that makes warm air rise. And when it rises, it pulls with it moisture. So rising warm air is moist air, but when it gets to 20,000 feet, the warm moist air is 20 degrees colder. And that means it can't hold on to the moisture that it picked up from its rise, whether it's a forest or a lake or grassland. The rising warm air is containing what they call a parcel of moisture that is related to the temperature. When it gets up to 20,000 feet, it has to give off some of the moisture because the moisture is too heavy. It turns from a vapor to a condensate. When it turns to a condensate instead of a vapor, it becomes visible. That visible moisture that is actually falling out of the warm air is what we call a cloud. So a cloud is a picture of the water content and the relationship between the water content and the temperature of the rising warm air. If the cloud is building vertically, then that means that the warm air below is dominant. If the cloud is building horizontally, then that means that the coldness of the earth is dominating and pulling the moisture down. When a cloud, yes.
Is that seasonal?
No, that's all the time.
Okay, gotcha.
That's all the time. So if you see a cloud that's horizontal, you know that the warmth, there's not enough warmth to get it to lift.
Gotcha.
If you see one that's like a cauliflower head, then you know that there's a lot of warmth carrying it, overcoming the cold. Mm-hmm. This principle of warm air rising, carrying water, going up and losing temperature creates a condition where the vapor, which is invisible, becomes visible as a condensate. And that's then a cloud. And the form of the cloud tells you the ratio of warmth to water. Water wants to condense, and the heat wants to vaporize it. So there's a play, there are all kinds of formulas and all kinds of theories about it. But basically that's what a cloud is like the foam on a glass of beer. It appears out of the fact that there's all this stuff rising below it. So that's a cloud. But in that pattern, there's something very interesting. So if I have warm air rising, if I'm here at the base of a mountain and the warm air is rising, the pressure around me, if I had a barometer, would be much lower than it is on the other side of the mountain. And the reason for that is that as the warm air rises up over the mountain and cools, the cold air that's descending is dry and cold and will come down. And because it's cold, the air mass hugs the ground. On the other side, on the low, the air is rising above you and there's less air around you. That's that warm and cool pattern creates what's known as low pressure and high pressure. High pressure is the result of cold air descending. Low pressure is the result of warm air rising. And when the warm air rises, the area where it's rising has low pressure and moisture is rising and spreading out into a cloud or into a global weather system. So on the null school map, when you have a ridge that's clockwise, that means that there is cold air coming from about 60,000 feet down into that circulation. And we're going to go there in a moment. But that's a difficult thing to understand because there's a very curious thing. I'll explain to you what that is. It's called the Coriolis effect. But if you wish to understand the winds and the weather patterns that are maybe 1,000 miles or 2,000 miles to your west, these air pressure movements are necessary. So air pressure on the surface is like a roller gears in a transmission. So suppose I have a high pressure area that's somewhere over, say, Iowa. And that wind in Iowa is rotating clockwise around a center in Iowa because it's high pressure. And that's a bubble or a mountain, or the meteorologists call it a ridge. So high pressure forms a ridge of air that sits down on the ground and blocks the path of the jet stream. So here we have, this is a map of 3 high pressure areas that are known to be very consistent by meteorologists at all seasons. But they're not always in one place. They're called semi-permanent ridges or semi-permanent highs because these ridges are connected like kinks in a hose. So if I had a wind coming in here and going around this clockwise circulation, it would go up and then come down, but now it's bumping into this one, so it would go up and then come down and then go up and come down. When it came down, it's starting to form low pressure around the high pressure. And in some seasons, these are placed here. In some seasons, they move this way. In some seasons, they move that way. If you look on the null school map, you can see when this one gets big, that one gets small. They are connected by thousands of miles of air. So your weather here is dominated by the high here. If this gets big and goes to the north, it pushes the jet stream up in the polar regions and you get it cold. If this high moves west, then the jet stream comes in at a lower angle and you get very benign weather. And that's your 5 day outlook. You can begin to look and see, how is this getting big? Is it getting small? Is it moving left? Is it moving right? And that pattern will allow you to determine where the continental jet will happen. So there's a reason why the air coming down rotates clockwise, and that's called the Coriolis effect. It's a difficult thing to understand. I'll do my best to explain it, because if you get it, you understand a lot. So there's something called the conservation of momentum that drives this. So imagine you're in your vehicle and you have your lunch in a bag on the seat, and you're driving down the road and suddenly a deer comes out and you hit the brakes. Your car stops and you stops, but your lunch doesn't. Your lunch comes off the seat and whacks into the dashboard, because your lunch is conserving the momentum of your forward motion. So anything in the northern hemisphere that is moving with the earth, especially suppose I have something at the equator, if I have, if I'm at the North Pole and I'm standing on the North Pole and the earth is rotating, I'm not moving through space. I'm rotating, but I'm not taking a lot of time to move through space. If I'm on the equator and I'm standing there, the earth is rotating very fast and I'm moving with it. If I am in an airplane here on the equator and I want to go up into Minnesota, and I go on a path due north, I'm not going to get to Minnesota. And the reason is that the equator is moving much faster than the pole. So I have to augment and change my due north track for my airplane to move to the right, because my target is moving slower than the momentum that I am at on the equator. It's a difficult thing, but what that does is that makes my straight line has to go to the right. If I'm up at the pole and I want to go to the equator is moving much faster than my original velocity, and I move to the right.
Dennis, a question, please.
Sure.
I don't know what your aviation background is, but you're saying that when these planes fly, this is computed.
Yes.
Yeah.
That's what a flight engineer would do.
Gotcha.
Yeah. So a flight engineer would figure out how much of a vector they would have to give off of an original flight plan in order to hit the target.
Right. Gotcha.
That's
interesting.
Yeah, that's what everybody's doing up there, is figuring out, and then you get a headwind and then the other vectors coming in. Yeah. So everything in the northern hemisphere that travels in a straight line is veering to the right.
Gotcha. Wow.
Yeah, and that's kind of a big ticket item there, but so if I have air that is rising off of the equator, it's going to want to move to the right. If that air is then falling down, it's going to move to the right.
Mm.
So imagine I have from the equator a parcel of air that's rising all the time because on the equator is where I have the most input from the sun. That's where the warmest air is. So at the equator, the upper atmosphere is 60,000 feet. At the pole, the upper atmosphere is around 10,000 feet.
Mm.
So I have a large parcel of warm, moist air rising off of the equator all the time. That rises to 60,000 feet and it cools very rapidly because 60,000 feet is like minus 60 Fahrenheit, really cold. And that cold air starts to descend at about 30 degrees north. 30 degrees north is Miami, Florida. So that means in that area of the Gulf of Mexico and Cabo and Baja, there's a stream of cold air coming from very high down towards the earth and spinning to the right. So that's what the map is showing, is that these semi-permanent high pressure areas are receiving a downdraft from 60,000 feet of cold air that is descending and hitting the surface of the earth, but it's also spinning to the right. And that means that on the earth, the spinning to the right is going to create a condition where the winds are blowing out and that parcel of air that's coming down off of 60,000 feet is going to tend to lodge on the earth rather than moving around with it. So that becomes then a semi-permanent high pressure area that rotates. And on the earth, meteorologists recognize that there's one over Hawaii, a semi-permanent high over Hawaii. There's one over the Western Pacific. There's one over the Western Atlantic, and there's one off the coast of the Azores. And they're like roller gears, continually getting large and small and large and small and moving east and
Oh, yes.
west, yeah, to create weather. This is then climate.
Dennis, are they always over the water?
No, there's one over Eurasia that is over land that is right now dominating even further out in the Western Pacific because it's so cold and covered with snow. Nothing's going to budge that puppy. It's over land. So the ones that are over water are a little more mobile because of the ability of the ocean to move warm and cold water around.
Mm-hmm.
So the thing that's feeding, whether or not the high grows or not, is sea surface temperature below it. There's something called ocean air linkage that people study when they want to study El Nino and things like that.
Okay.
Yeah. So I have a return cycle of cold air coming down to create these highs here, but I also have one at 60 degrees north coming down. That's called the polar vortex. And the polar vortex has been kicking your butt this year. That's a high pressure area at the pole that's very cold.
Yeah.
And sometimes there's an abundance of warm air that goes up and forms at 60 degrees north and 90 degrees north a very strong ridge up there that breaks out through the Bering Sea. And when that happens, it's creating a jet into the global circulation that makes eddies. Those eddies are storms. And the eddies that are created up here by the polar front spin out of the Bering Sea, they spin out of Canada, they spin out between Greenland and they make their way down around and create weather along something called the jet stream. So the jet stream is a river of air that's like a rotating horizontal column of air moving about 400 miles an hour. And that is streaming the storm track. Okay, so the jet stream is what we're trying to track with this, because the jet stream is what delivers to you what's known as continental air. But your continental air comes from the ocean here and pushes up and then goes down. And depending upon how it operates, we either get benign weather or terrible weather. This and that pattern is rotates every 4.5 years, or every 9 years, or every 10 years. They call it decadal influence. So every 10 years or every 20 years, you get a return cycle of very predictable weather patterns. So if you look back in your records about when you have a lot of nor'easters come, you'll probably find maybe 5, 10 years, 20 years, if you keep records like that, that there's a return cycle for really, really bad weather. And then over the years, not so much. And that's what I think eventually we could do. I could show you some things. That was 30 years of research that I did trying to go a year out. I have many, many, many charts of upper air to do that. It's possible to actually predict trends that way down the road. But for now, that's just the pattern, what they call a global circulation. So the global circulation for your area has a great deal to do with the oscillation of the Atlantic high and the Hawaii high moving west and moving east, blocking the jet stream.
Mhm.
Okay.
Yep.
Yeah. So what I'd like to ask you to do is I'm going to work on that video of the clouds that I made. There have been some really nice cloud sequences here, and I'd like to send that to you so you can kind of look at it and look on the null map. Try to get in the habit of like checking that for 5 minutes, 4 minutes in the morning, and just kind of surf around on it. So you can get familiar with these larger air masses. I mean, I could describe to you small movements, but the small movements you'll do better with weather underground. You know, that's a 2-day micro whatever with tons of gear that people are sending to you. But if you really want to develop a weather eye, that null map will cause you to kind of muse about what the heck is going on out there over Spokane, Washington, or what's happening over Kansas. So it's updated every 3 hours. It's not actually a real-time map. It's kind of presented as real time, but it's accurate with regard to the NASA data that's being fed into it. There's a huge amount of data that's going into the forming of that map. I know many people who teach meteorology are using that map to teach. It's very,
Okay.
it's really,
That's a
it's
great
really a very interesting thing. Once you get a handle on big air masses and how they are moving, then the small air masses make a lot more sense. That's why I'm kind of going there with these larger movements, because when you begin to track wind, when you begin to track clouds and you have a picture of the larger air mass movements, your weather eye gets extended about 2,000 miles to the west. That's what I want to do for you.